In the textbook, we've given the equations for the reflection and the transmission matrices when we were doing eigenmode expansion of the scattering at an interface between two waveguides. But we've derived these equations under the conditions that the basis functions, the eigenmodes, are orthogonal. Question in this exercise is, what do these equations look like if your basis functions are no longer orthogonal? Can you rewrite the equations in terms of block matrices? So pause the video and see if you can figure this one out. So let's go back to the equations that we have in the textbook. So these equations basically express the continuity of the different components of the electromagnetic fields when you have an interface between two media. So let's say you have a first waveguide, waveguide 1, and then you have a medium 2 with a second waveguide. And then what you're doing is you're exciting this first waveguide with a mode, let's say a mode with index P. So we have EP in medium 1, which also has a magnetic component. So you hit that interface with that particular mode, and that will give rise to a transmitted field. A transmitted field which you will then expand into the eigenmodes of the second waveguide. And the expansion coefficients, we will call these the transmission coefficients. So for example, this coefficient, we can call that transmission to the first mode in the second medium when we excite it with the pth mode in the first medium. And then we have a set of transmission coefficients up to n. So every time we excite that with a certain mode P here. And then we do the same thing for the reflected field, which we can also write as a sum of the eigenmodes in the first medium and the expansion coefficients. We call these reflection coefficients. So again, when we look at the coefficient in the expansion that corresponds to the first mode, we have R1, and because we excite it with mode P, we have an extra P there. And then we have RNP. So when we excite with a certain mode P, we have n transmission coefficients and n reflection coefficients. And what we have here is basically also two n equations for these two n unknowns. Because these two equations here, we can write them down for all possible values of I going from 1 to n. So for excitation with a single mode, we have enough information to calculate the n transmission and the n reflection coefficients. Of course, in order to describe that interface in the most general form, we should also figure out what happens when we do not excite with the mode P, but with an arbitrary mode. So this P should also vary from 1 to n. So this whole thing, this whole procedure, we should repeat that also n times for n different excitation modes. So rather than having n reflection and n transmission coefficients, if we do that n times for the different excitations, we have a matrix, an n by n reflection matrix and an n by n transmission matrix, both n by n, which describe the scattering that's happening at that interface. In the course notes, we've used orthogonality between these different modes to come up with a set of simpler equations to calculate the R and the T. Basically, what you needed to do was solve an n by n system of equations. Question is, if you're now not allowed to use the orthogonality, but you're basically stuck with these equations over here, which is enough because you have enough equations and enough unknowns, but can you write these in a more compact form using block matrices, which will involve the overlap matrices? So for example, quick reminder, if we have an overlap matrix between the second waveguide and the first waveguide, denote it like this. So this is actually a matrix. I should write it like this. And if we have the ijth component of that matrix, this is defined as an overlap integral of the electric field in the second waveguide. So this 2 corresponds to that 2 over here with the magnetic field in the first waveguide. So again, 2, 1, 2, 1. And then the ij is here, the ith electric mode and the jth magnetic mode. So this is how these block matrices, these overlap matrices are defined. Question is, using this definition and similar definitions for overlap 1,1 and overlap 2,2 if you want, can you use these definitions to write down this thing in a much more compact form, which is more easily solvable on a computer? So pause the video and see if you can achieve that goal. So what we're going to do is we're going to look at each of the terms in these equations and see if we can write them as a certain element of a matrix which will involve these overlap matrices. So let's focus our attention on the first term here for the first equation. So the first term of the first equation is the overlap of modes in medium 1 with mode in medium 1, and that's P here and I there. Now, by definition, almost, you can write this as an element of the overlap matrix between modes in medium 1 and medium 1. Which element of that matrix? Well, it is the P'th element. Okay, so that's just straightforward definition of the overlap matrix. Let's have a look at the second term. The second term is a bit more complicated. It's a sum over J of the reflection coefficient Jp here. And then we have the overlap H1, H1I. Okay. If we now bring in our overlap matrix, we can write this as a sum over J. Now, in terms of our overlap matrix, it's the overlap matrix, again, between medium 1 and medium 1. And we're looking at the J'th element of that matrix, and then we multiply by our Jp. Okay, so far so good. This looks suspiciously like a multiplication between two matrices, but something is off. So let's have a look again at how we multiply matrices. Quick recap: if you have a matrix A, which you want to multiply by matrix B, and you're interested in the ijth element of that product, the way you do that is by having a summation over a summation index k of A, I, K, B, K, J. So again, quick example, if you have a 2 by 2 matrix which you want to multiply by another 2 by 2 matrix to give you a 2 by 2 matrix, and you're interested, for example, in this element here, which is the 2, 1 element, the way you do that is by multiplying this row here with that column. So it's the second row and the first column. So you indeed see that you sum over an index here, which is in the middle, if you can call it like that. So this k here is nicely sandwiched between the I and the j. So it would be nice if we were able to apply that also to our expression over here. But you see that the summation index j is not really nicely sandwiched in the middle here. This order is wrong. Well, wrong is not useful for our purposes here. Luckily, we can quickly change that by just transposing our matrix. So we have the sum over J, then we have the overlap integral 1, 1 transposed. And now this time we no longer have the J'th element, but the ijth element. So we have ij, reflection matrix Jp. And now we can indeed write that as a certain element of the product of two matrices. What are the two matrices that we take the product of? It's O1, 1 transpose reflection matrix. Of course, if I want to be really accurate, I should indicate that these are matrices, but I'm a bit sloppy here. So it's these two matrices that we take the product of. But then we have the IP'th elements, so we have IP. Okay, good. So what we've done is we have that second term, which we've written as the IP'th element of a certain matrix. The first term we have written as a P'th element of a certain matrix. So it would be nicer and a bit more consistent if we were also to write that not as the pith element, but as the ipth element. Luckily, simple transpose is all it takes to also have an ipth element here. So to have a sneak preview at the strategy that we're going to use, what we want to do is write each of the terms of the equations as the ipth element of a certain matrix. So we've done that for the first term. We've also done that for the second term. We have the ipth element of another matrix. If we can also do that for all of the other terms, then it basically means that, okay, if the ipth element of all of these matrices are the same, then it basically means that the matrices themselves should also be the same. And that's a way to write this in a much more compact way, so that we don't need to explicitly mention that I and P loops from 1 to n. We're almost there. We just need to do that for the third term. Now that we know how that's done, that should be pretty straightforward. So we have a sum over J transmission JP, and then an overlap integral like so, H1I. Okay, so this is the term that we need to massage to get this overlap matrix there. So this gives us a sum over J of an overlap matrix between medium 2 and medium 1. And we have the, let's see, we have the, so we need to have the J nicely sandwiched in between. So we have TJP here. So now we have the J in front, so we should also transpose that matrix so that we can have basically an ijth element here. And then if we do that, we can write that as an element of a product of two matrices. So we have the overlap between medium 2 and medium 1. We transpose that, we multiply that with the transmission matrix, and then again we have the ipth element. So if all of the ipth elements of these matrices are the same, that means that the matrices themselves are the same. So let's just copy them over. So for our first term, we have the overlap integral 1,1 transpose. So that's our first matrix. Overlap integral 1,1 transpose. For our second, we have over here, we have the overlap integral 1,1 transpose reflection matrix. So overlap matrix 1,1 transpose reflection matrix. And then finally, for our right-hand side, we have the overlap integral 2,1 transpose transmission matrix. So after all of these calculations, we have a much more compact way of representing that first equations for all of the different values of I and P. So now that you know how it's done, pause the video and try to do a similar operation on the second equation. And then once you have that, see if you can combine these two equations into a single whopping big equation. Right, let's have a look at the first term of the second equation. So which is EI1HP1, and that of course is an element of an overlap matrix between medium 1 and medium 1, and it is the ipth element. Okay, moving on to the second term, that's going to be a sum over J of RJP and then overlap 1H1J, and that we can write as a sum over J of an overlap matrix between fields in medium 1 and medium 1, an ijth element, and then we have RJP. And this is just the ipth element of the product of these two matrices. So we have overlap 1 reflection I pth element. No need to have transposes at this point in time, so that's convenient. And then finally, for the last term, we have again a sum over j transmission coefficients in this time. So transmission jp, we have the overlap 1hj2. Okay, so this we can write as a sum over j, the overlap between 1 and 2, the ijth element, transmission jp. So the j is nicely sandwiched in the middle. So we can write this as the ipth element of which matrix? The product of the overlap between 1 and 2, overlap matrix 1 and 2, multiplied by the transmission matrix, the ipth element. So again, now it's just a matter, since all of the ipth elements of these matrices are the same, we can just conclude that the matrices themselves are the same. So we have that the overlap matrix 1, 1 plus, let's have a look. It's a minus sign indeed, so we have a minus rather. So minus what we have up there, the overlap between medium 1 and medium 1 multiplied by the reflection matrix is the overlap matrix between medium 1 and medium 2 times the transmission matrix. Okay, a lot of work, but we finally arrive at this equation over here. So now we have two equations that look a little bit similar. Remember, what we're after are the matrices R and T. So actually we can consider this as two equations for two unknowns in terms of matrices, namely the R matrix and the T matrix. So we can write this as a big system matrix for unknowns, let's say T and R. So finally we can write this as a huge matrix where we have here the unknowns, the T matrix and the R matrix. We write that in a format like this. So if we do that, let's have a look at what we need to do here. So for that equation, we should bring, let's say, R to the other side, and then let's leave this one as the left-hand side, and then flip the order. So this is the coefficient of T, and minus that one is the coefficient of R. So that gives us this first row in that matrix. It's the overlap between 2 and 1 transpose. And then we have minus the overlap 1 and 1 transpose. Okay, 2 and 1 transpose, that's right. And then for the right-hand side, it's the overlap 1, 1 transpose. Okay, overlap 1, 1 transpose. And then finally, we do something similar for that equation over here. So the coefficient of T is the overlap integral between 1 and 2. And then we have plus, and then we have the overlap matrix between 1 and 1. And then for the right-hand side again, overlap matrix, I should say, between 1 and 1. So quick check to see if that's right. That seems to be right indeed. So these are then the system equations that you can use if you no longer have orthogonality between your eigenmodes. But if that's the case, there's a big price to pay, because if you now look at the dimensions of this matrix, for example, it's a 2n by 2n system matrix as opposed to an n by n system matrix. And also here on the right hand side, we have a 2n by n matrix. So it's a lot more work compared to solving the n by n system that we have when we do have orthogonality. So if you do have orthogonality, it would be really stupid to do it like this, because that basically is a lot more calculation intensive. It's basically if you double, at least if you do it naively, if you double the size of your matrix, then this thing scales with a factor of 8. So if you have orthogonality, please use it.